Welcome to Algeomulus Prep Academy. Today, we'll be learning about finding points of inflection using the second derivative. So, what is a point of inflection on a graph? An inflection point is a point on the graph of a function at which the concavity changes and a tangent line must exist. Therefore, if f double prime of x changes signs at x is equal to a, meaning f of x changes concavity at x is equal to a, and f has a tangent line at x is equal to a, meaning f is continuous at x is equal to a, then there's a point of inflection at x is equal to a. Also keep in mind, an existence of a tangent line must be proven. So, why a tangent line? Well, f needs a tangent line at x is equal to a to prove that f is continuous at x is equal to a. Therefore, if there is not a tangent line of f at x is equal to a, then we know that f of x is not continuous at x is equal to a, meaning there could be no point of inflection at x is equal to a. Now let's get on to some examples.
Example 1 is asking us to find all the points of inflection of 7x to the power of 4 plus 8x cubed plus 2x squared plus 9x. We first must find the first derivative of the given f of x. We do this so we can take the derivative of the first derivative, also known as the second derivative. Then we find the second derivative of the given f of x. The second derivative of the function allows us to learn about the concavity and points of inflection of the f of x graph. So we set f double prime of x to 0 and undefined and solve for x. We need to find the critical numbers of f double prime of x to identify possible points of inflection at these critical numbers. So we create a number line with the critical numbers. Plug in numbers on intervals negative infinity to negative 0.4701 and the next interval is negative 0.4701 to negative 0.1013, and the final interval is negative 0.1013 to infinity into f double prime of x to find the sign of each interval. If the sign changes at each critical number, then that means there is a change in concavity at the critical numbers. Thus, that critical number represents the x value of an f of x point of inflection. Since both of the critical numbers have f double prime of x change signs, they are both considered the x values of f of x's points of inflection. Now, we plug each critical number into f of x and solve. The points of inflection for f of x are the x value negative 0.4701, y value negative 4.2786, and the final point is negative 0.1013, negative 0.8986. You solve for the y value of the specific x value to find an exact point of inflection, not just an x value. F of x has a point of inflection at x is equal to negative 0.1013 and x is equal to negative 0.4701 because f double prime of x changes signs, that is f of x changes concavity, and f of x has a tangent line at these points. F has a tangent line at these points because f double prime of x exists, therefore f prime of x exists, and therefore the tangent line exists. In example 2, we are asked to find the x values of the point of inflections for the function f of x is equal to 6 over 5 cube root x plus 2. First, we have to find the second derivative, find the first derivative, then take the derivative of that function to get the second derivative. We find the second derivative is equal to negative 4 over 15 cube root x to the fifth power. Then set the second derivative equal to undefined to find the critical points. To do so, set the denominator equal to 0 because a number over 0 yields undefined. By setting 15 cube root x to the fifth power equal to 0, we find that f double prime of x is undefined at x equals 0. Then set f double prime of x equal to 0 to find the other critical points. To do so, set the numerator equal to 0, since negative 4 never equals 0, f double prime of x is never equal to 0. Next, make a number line to show when f double prime is positive, negative, and changes signs. To find where f double prime is positive and negative, set f double prime of x equal to a number greater than and less than 0. We set f double prime of x equal to negative 1 and find that f double prime of negative 1 yields a positive value. So f double prime of x is positive when x is less than 0. When we plug in 1, we find that f double prime of x is negative, meaning f double prime of x is negative when x is greater than 0. There must be a tangent line at x equals 0 in order for a point of inflection to occur at x equals 0. In order to prove that a tangent line exists at x equals 0, you have to prove continuity exists at x equals 0. Find f of 0 and the line x approaches 0 from both sides. We find that f of 0 exists, limit as x approaches 0 exists, and that f of 0 is equal to the limit as x approaches 0 of f of x. Thus, f of x passes the continuity test at x equals 0 and is continuous at x equals 0. F has a point of inflection at x equals 0 because f double prime of x changes from positive to negative, and f has a tangent line at x equals 0 because f of x is continuous for all x equals 0. Thus, the function f of x is equal to 6 over 5 cube root x plus 2 has a point of inflection at x equals 0. In example 3, we are asked to find the x values of the points of inflection for the function f of x is equal to 3 over 2x plus sine x over the interval negative 3 to positive 3. First, we have to find the second derivative, and to do so, find the first derivative and then take the derivative of that. We find out that the second derivative is equal to 3 over x cubed minus sine x. Then, set the second derivative equal to 0 to find the critical points on the interval negative 3 to positive 3. Type in f double prime of x into the graphing calculator and set the window to negative 3 to positive 3 for x. Then we use the 0 function to find when f double prime of x is equal to 0. We find that f double prime of x equals 0 when x is equal to positive and negative 1.44660074. Then find when f double prime of x is undefined to find the other critical points. F double prime of x is undefined when the denominator x cubed equals 0, meaning f double prime of x is equal to 0 when x equals 0. Next, make a number line to show when f double prime of x is positive and negative, so you can clearly see when f double prime of x changes signs. By looking at our graph, we can see f double prime of x is positive from negative 3 to 1.44660074 because f double prime of x is above the x-axis. Then it changes to negative, back to positive, and then back to negative. F has a point of inflection at x is equal to negative 1.44660074 and x is equal to positive 1.44660074 because f double prime changes from positive to negative and f has a tangent line at these points. Because f double prime of x exists at this point, so f double prime of x exists at this point. F does not have a point of inflection at x equals 0, even though f double prime changes signs at the point. There is no point of inflection because there is a vertical asymptote at x equals 0, because f of 0 is equal to 3 over 0, which is a number of 0, which, by the vertical asymptote theorem, means that there is a vertical asymptote at x equals 0. Therefore, f is not continuous at x equals 0 because of the vertical asymptote, so there is no tangent line at x equals 0, so there is no point of inflection. Thank you for watching an Algeometrics Prep Academy video. Remember to like and subscribe.